Hey guys, so this is the last video of Unit 3. It's video 3 of Unit 3. And we're going to talk about elevator problems, which really is just vertical net force problems. Okay? Alright, let's get started. This should be a pretty quick video, hopefully. Alright, so to start, I just want to make sure we review a little bit from the previous lecture. Okay, so after today, you should be able to draw a free body diagram for an object that has a changing vertical net force and solve for problems that involve vertical acceleration. Remember, a non-zero net force means that the object is accelerating. Okay, if the net force is zero, then the object is either going at a constant speed or it's not moving. All right, friction opposes motion, always, okay? And the coefficient of friction is a measurement of how sticky or smooth a surface is, and is different if an object is at rest or moving. Remember, kinetic and static. So at rest was static, moving was kinetic. All right, elevator problems. Any object that is accelerating in the upward or downward direction will have a non-zero net force. Think about what you feel when an elevator starts accelerating upward and downward. So first, I just want you to think about that. When you're standing in an elevator and it starts to accelerate upwards, do you feel heavier or do you feel lighter? Okay, and the answer should be that you feel heavier, right? Because the elevator is pushing up on the bottom of your feet, and you should feel heavier. Now, if you're at the top of the building and you accelerate downward very quickly, right, then you should start to feel lighter because the floor basically removes itself from under you, okay? Now, if the elevator cable broke, and that's what this little picture is, it's kind of a cute little demonstration of this. So if you are just going at a constant speed, you would feel normal. If you were accelerating upward, then you'd feel greater than your normal weight. And if you were accelerating downward, you'd feel less than your normal weight. And then if the cable broke, you would have no weight, and both the elevator and you would be dropping at, the acceleration of gravity at 9.8. You'd be in free fall, okay? All right, so that's kind of the idea. So you got to kind of keep that in mind. All right, now example 1 says draw a free body diagram of an elevator accelerating upwards. So I'm going to just draw a separate box here. Now if an elevator is accelerating upward, then it has weight down, and the upward force is going to be bigger than the force of gravity. Okay. All right. And that's because it's accelerating up, and that's what that picture shows us, all right? Now, you can imagine that if the elevator is accelerating upward and you're standing in it, if we were to draw your free body diagram, right? So if we draw so this is the free body diagram of the elevator. Of the person, it would look the same, but we would just name this differently. So if this is the person, they have weight, right? And then the upward force is actually the normal force of the ground of the elevator pushing up on the person. Okay? That's the upward force on the person. The elevator, it's probably like a tension force, it's probably the cable, but on the person, it's just the normal force from the ground pushing up. Okay? So usually in these problems, the upward force is the normal force. All right, so example, a girl with a mass 55 kilograms is in an elevator. The scale she is standing on measures the normal force of the floor, okay? So the scale measures the normal force. Draw a free body diagram, okay? She's just standing there, so we'll have force of gravity, and we'll draw the normal force being equal, okay? Force of gravity on the girl. Well, force of gravity on anything is mass times acceleration of gravity. So we get 55 times negative 9.8. So negative 539 newtons. Okay. If the elevator is not accelerating, what does the scale say? So she's just standing still on it. Her weight is pushing down with 539 newtons. If she's not accelerating, then that means that the scale has to push up with the exact same amount in order to keep her from falling through the scale. So in that case, the force of normal force equals the force of gravity, and so it's 539. And we just say positive because normal force is upward. Okay. Now, if the scale now reads 850 newtons, so basically what they're saying is that the normal force is 850 newtons. So the floor is pushing up more than her weight down. What is her F net? Well, if the normal force is 850, her weight didn't change. It's still 539 down, right? And you can put negative. But when we plug it into the equation, positive is 850, negative is 539. And so the F net is just the difference of those two. So you get 311 as her net force. Okay. All right. Now for E, what is her acceleration? Well, the net force is 311. F net is always equal to ma. So if we know the net force is 311, we know her mass is 55, then we can solve for A. Then I get 5.65 meters per second squared. Okay. Now for part F, it says if the elevator now accelerates down at -3, so A is -3, what is the F net? So F net always equals ma. So F net would equal 55 times -3. So it'd be -165 newtons. Okay, so that's the F net. What would the scale now read? So they're asking us for Fn. Well, we know that F net equals positives minus negatives. We know that F net is -165. We're looking for normal force. And we know gravity is 539. We found it before. So all we do is we add 539 to the other side. And we get 374. Now, let's make sure that that makes sense, right? If we look back at our free body diagram, does it make sense that her normal force is less than the gravity force if she's accelerating downward? And that should make sense to you, right? It'd be like this. Downward force would be 539. Upward force would be 374. And so, yes, they should accelerate downward. Okay? And that's actually the end of that one. It is a quick video. We will talk more about it in class. But you are good. All right, makes up for the last long video.